glow of the monitor is probably, the only light in your room right now.
Yeah, that's usually how it goes.
Right. You've got a terminal window open, maybe a cup of coffee that went cold an hour ago, and you are tuning in to level up your AI knowledge. We see you, software engineers.
Welcome to the late shift.
Exactly. Consider this an exclusive late-night deep dive into a stack of really fascinating notes we've pulled from the LLM Mastery series. We are focusing specifically on building a tokenizer from scratch.
Which is, honestly, the most crucial part.
It is. We are going to demystify the absolute very first step of how large language models process text. Because before an AI can generate like a brilliant block of Python code or debug your deployment script.
Or even write a coherent sentence.
Right. Before any of that, it has to do something completely invisible. It has to chop your prompt into numbers. So tonight, we're opening the hood on the tokenizer.
It really is the invisible gateway, you know? I mean, everyone in the field wants to talk about the massive neural networks.
Oh, absolutely. With billions of parameters.
Right. The parameters, the self-attention mechanisms, all the flashy stuff. But none of those complex architectures ever see a single word of raw text.
Wait, really? Not a single word?
Not one. They only see numerical IDs. And the system that translates your string of text into those numbers, the tokenizer, is arguably the most critical and, well, overlooked bottleneck of the entire machine learning pipeline.
Okay, let's unpack this.
Yeah.
The notes from the LLM Mastery series use this brilliant analogy to set the stage. They say tokenization is exactly like the lens on a camera.
It's a great way to picture it.
Think about it, right? The photographer, which in this case is the LLM itself, the massive neural net, gets all the glory.
Of course.
The photographer gets the magazine covers, the hype. But if the lens attached to that camera is, I don't know, scratched or warped or completely out of focus.
It does not matter how much skill is behind the camera.
Exactly. The picture's going to be ruined.
That analogy holds up beautifully when you look at the mechanics, too. The lens fundamentally dictates how the reality of a scene is captured and projected onto the sensor.
So the LLM is the sensor.
Yeah, exactly. If your tokenizer is blind to certain nuances in the text, or if it chops up a programming language's syntax in a bizarre, unnatural way, the LLM sensor receives distorted data.
Garbage in, garbage out.
Pretty much. And that is what we are exploring tonight. How this foundational lens is manufactured from scratch and why its design dictates, well, absolutely everything that follows.
So if we're going to grind the glass for this camera lens, we have to start with the raw materials.
A raw text.
Right. We need to look at how a tokenizer first approaches a giant raw block of text before it does anything mathematically complex. And looking at the source notes, there is a massive, almost hidden assumption in the pre-processing stage.
Oh, the word splitting assumption.
Yes. The subword algorithms we're going to get into, the engines of the tokenizer, they assume that you can meaningfully split text into words first.
And only then apply subword merging within those specific words.
Wait, splitting into words first. As an engineer, assuming a clean split by space or punctuation seems incredibly fragile to me.
It's a nightmare waiting to happen.
I mean, my mind immediately goes to parsing poorly formatted CSV files.
Oh, man. The dreaded CSV parser. We have all been there.
Right. Anyone who has written a script to ingest a massive, messy CSV file knows exactly what I'm talking about.
Yeah.
You assume the delimiter is a comma,
Naturally.
but then some user typed a comma inside a text field without escaping it, or there's a row newline character.
And suddenly your perfectly structured columns are shifted by one.
Exactly. The data types are entirely wrong, and the rest of the parsing fails catastrophically. So if a tokenizer assumes a space equals a word boundary, aren't we setting ourselves up for that exact same parsing failure right at the starting line?
This raises an important question, and your skepticism hits on a major issue in natural language processing.
Because it's not always just clean spaces, right?
No, not at all. When you are dealing with English, or most European languages, splitting by spaces and standard punctuation generally works. It is a convenient heuristic. But what happens when the tokenizer encounters languages without clear word boundaries? Consider Chinese, Japanese, or Thai. Spaces are not traditionally used to separate words at all in those languages.
Oh, wow. So if the rule simply looks for a space, it would just see an entire paragraph as one giant unbreakable string.
Exactly. It would just be a massive block. And the problem gets even more complex when you look at highly agglutinative languages.
Okay, pause. Agglutinative. For the software engineers listening who haven't taken an advanced linguistics class, what does that actually mean in practice?
Fair point, sorry. Think of languages like Turkish or Finnish. In an agglutinative language, you basically glue prefixes and suffixes onto a root word to convey complex meaning.
So instead of separate words.
Right. Instead of using separate words to say, in my houses, Turkish might use a single word like evlerimde.
I'm probably going to butcher the spelling in my head, but okay.
Well, evembe is house, evler makes it plural, im means my, and de means in.
Wow, all in one word.
Yes. If a tokenizer blindly splits by spaces, it treats that entire complex structure as a single atomic unit. It entirely misses the internal grammatical logic that a language model desperately needs to learn.
That makes total sense. And
Correct.
honestly, we don't even need to look at foreign languages to see this problem. We see it in software engineering every single day.
Oh, for sure. With code syntax.
Exactly. Think about a massive camel-cased variable name like fetch user data from database.
Or a complex regular expression string.
Right. Or a block of minified JavaScript where all the white space has been intentionally stripped out.
That is a fantastic parallel. If your pre-processing rule simply looks for spaces, it is going to treat that minified code or that camel-cased variable as one massive unbreakable block.
Which totally ruins the tokenization.
Completely. This initial word-splitting step is a critical bottleneck. The subword algorithms we rely on assume they're operating on isolated pre-chunked words.
So if that pre-chunking is flawed,
if your initial delimiter assumption is wrong, to use your CSV analogy, everything the tokenizer attempts next is compromised. The lens is already starting to warp before the AI even opens its eyes.
okay, so let's say we have navigated that minefield. We have somehow chunked our text into what we are at least calling words, whether that is through spaces or language-specific rules or regex.
The pre-processing is done.
Right, now we enter the engine room. How does the tokenizer actually compress and break down those words into the final tokens the AI will ingest?
This is where the heavy lifting happens.
The notes highlight two heavyweight algorithms that dominate the field: byte pair encoding, or BPE, and word piece, which was, developed at Google and famously used to train BERT.
Yep. Two very different philosophies, though.
And both of these take what the notes call a bottom-up approach.
Yes. The historical approach used to be top-down, trying to use massive dictionaries and complex grammatical rules to slice words apart.
Which sounds incredibly tedious.
And brittle. It proved far too brittle. The bottom-up approach completely flipped the script. These algorithms don't start with whole words.
What do they start with?
They start with the smallest possible units, individual characters or raw bytes, and they iteratively merge them together to build larger and larger subwords based purely on the patterns in their training data.
Here's where it gets really interesting for me. When I read about this bottom-up merging process, it instantly reminded me of refactoring a massive, messy code base to find the most frequently used helper functions.
Oh, I like that. How so? Walk me through the mechanics of that.
Well, imagine you are an engineer reviewing millions of lines of raw, unoptimized code. At first, you're just looking at individual characters and basic syntax.
Right, just a sea of characters.
Exactly. But as you read, you notice a specific sequence repeating over and over. Maybe it's a very specific database call, followed by a data formatting loop.
And you don't want to keep writing that out.
Right. As a good engineer, you don't leave that raw code scattered everywhere. You abstract it. You merge those operations into a single efficient helper function and name it something like fetched-in format.
We're compressing it.
Exactly. You've just taken a sequence of smaller frequent units and merged them into a single token. But how does BPE actually execute that mathematically on raw text?
Let's apply your refactoring idea directly to the text. DPE starts with a vocabulary consisting entirely of single characters.
Okay.
It scans the entire training corpus and literally just counts the frequency of every adjacent pair of characters. Let's say it notices that the character E and the character E's appear next to each other more often than any other pair.
Like in plurals or words ending in "es."
Exactly. BPE says, great, I am creating a new rule. Merge E and es into a new subword token called es.
So it adds "es" to its dictionary.
Yes, it updates its vocabulary, goes back to the text, and replaces every E and es with the single token es.
So now "es" is treated as a single building block.
Yes. Then it runs the count again. Now, it might see that the character T and the character H appear together constantly. It merges them into the.
Okay, I see where this is going.
On the next pass, it might see that the new token the and the character E appear together frequently, so it merges them to create the token the. It is relentlessly, iteratively refactoring the text into the most frequently used subwords.
Wait, I am stuck on something here. If BPE is just scanning and counting pairs, isn't that just a brute force frequency counter?
That's exactly what it is.
It sounds almost too simple. How does WordPiece improve on that? The notes say WordPiece evaluates the likelihood of the data, but what does that actually mean?
It's a bit of a paradigm shift.
Like, how is it calculating likelihood before the language model is even trained?
That is the crucial distinction, and it is where WordPiece gets mathematically sophisticated. You are right, BPE is a brute force frequency counter. It only cares about raw volume.
Right, just counting pairs.
WordPiece, on the other hand, builds a rudimentary language model during the tokenization training process itself.
Oh, wow.
It doesn't just ask, how often do H and U appear together? It asks a statistical question. If I merge H and U into who, does it increase the overall probability of my model correctly predicting the rest of the training data compared to leaving them separate?
I think I need a concrete example of that. Why would leaving them separate ever be better if they appear together a lot?
Okay, let's say your training data has the word hug a million times, but it also has the word bug a million times and the word mutt a million times.
Yeah, lots of UG words.
Exactly. BPE might look at hug and see that H and U appear together frequently, so it just merges them into who.
Because it just saw it a million times.
Right. But WordPiece looks at the underlying probability distribution. It realizes that the sequence UG is incredibly highly predictive of the structure of the English language in your dataset.
Oh, I see.
If it merges H and U into who, it destroys that UG pattern. WordPiece calculates that keeping H, B, and M separate and creating a dedicated UG token actually makes the entire dataset more mathematically predictable.
So it is not just raw counting. It is actively evaluating the statistical value of the merge against the broader context of the language.
Precisely. It is a subtle shift in the mathematical criteria, from raw frequency to probabilistic likelihood, but it changes the entire foundation of the model.
It's a completely different philosophy.
It really is. The choice between BPE and WordPiece isn't just a syntax difference, it completely changes the shape of the tokens the model ultimately learns from.
Because BPE might make weird choices.
Yeah, BPE might give you a subword that is extremely common but linguistically nonsensical, whereas WordPiece, by focusing on probability, tends to prioritize merges that align slightly better with actual prefixes, suffixes, or root words.
So if you are listening to this and trying to choose a tokenizer for a custom dataset, you are essentially choosing between a highly efficient raw frequency counter and a probabilistic predictor,
You're choosing the physics of your model's universe.
dictating the very atoms of it. Which brings us to a massive, unavoidable collision with reality. Because if we just let these bottom-up algorithms run wild, whether it is BPE or WordPiece,
So we just keep going.
they could theoretically just keep refactoring and merging forever, right?
Yeah.
Eventually, an entire paragraph in your training data would just become one single massive token.
They absolutely would. They would perfectly memorize the training data by turning every sentence into a single token, and as a result, they would be completely useless for generating anything novel.
Zero generalization.
They would have zero ability to generalize.
So engineers have to step in and put a hard limit on the process. The algorithms need a stopping condition.
And that stopping condition is everything.
The notes point out that this leads directly to one of the most consequential design decisions in all of tokenization, the vocabulary size.
Yes.
The engineering dilemma of deciding exactly how many unique tokens your tokenizer should be allowed to recognize. Do we stop merging when we have 30,000 unique tokens? 50,000?
100,000.
It's a huge debate.
Yeah.
So what does this all mean for the software engineer actually building or deploying these models? To me, this looks like the ultimate classic software engineering trade-off between memory and compute.
If we connect this to the bigger picture, it is the exact fulcrum upon which the performance of the entire model balances. How do you visualize that trade-off?
Think about it like building a house with Lego bricks.
Okay, I'm with you.
If you configure your tokenizer to have a tiny vocabulary size, say you cap it at just 10,000 tokens, it is like restricting yourself to building a house using only the standard small 2x4 Lego bricks.
Just the basics.
Right. Now, the advantage is that your inventory is incredibly simple. You don't have to memorize thousands of different complicated pieces. The manual for your pieces is tiny.
The building takes forever.
Exactly. Because the pieces are so small, a single sentence might be chopped into 50 different tokens. It takes thousands and thousands of steps to build anything complex. Your sequence length, absolutely explodes.
And in the realm of large language models, an exploding sequence length is computationally brutal.
It kills the GPU.
It really does. The self-attention mechanisms in these models, the math that allows the AI to understand the relationship between words scale quadratically with the number of tokens.
Let's break that quadratic scaling down for a second, because that is a buzzword that gets thrown around a lot.
Sure. Quadratic scaling means that if you double the number of tokens in your sequence, the amount of compute required doesn't just double, it quadruples.
Wow.
Every single token has to mathematically attend to or look at every other token in the sequence.
So it's an exponential explosion.
Yeah, so if your tiny vocabulary chops a prompt into 1,000 tokens instead of 100, the processing time and the GPU compute required to understand that prompt doesn't just go up by a factor of 10, it goes up by a factor of 100.
That's insane. Long sequences just crush your compute budget.
They absolutely do.
Okay, so if long sequences are the enemy of compute, let's just go to the other extreme. Why don't I just define a massive vocabulary size? Let's make it 1,000,000 tokens.
Ugh.
Now, in our Lego analogy, I'm not using standard 2x4 bricks anymore. I have thousands of highly specific, custom-molded Lego pieces. I have a single massive piece that is an entire pre-assembled Millennium Falcon cockpit.
Right, one giant chunk.
A complex sentence might be represented by just 3 or 4 huge tokens. My sequence length is incredibly short. The math is easy. I'll just buy more RAM to hold the bigger vocabulary dictionary. Problem solved, right?
I love the instinct to just throw more hardware at the problem, but buying more RAM doesn't solve the underlying mathematical bloat.
It isn't.
No. That dictionary you mentioned is actually the model's embedding matrix. For every single token in your vocabulary, the model has to learn and store a massive vector of numbers representing its meaning.
Oh, right. It has to know what the Millennium Falcon cockpit actually is.
Exactly. Let's say your model uses a vector size of 4,096 dimensions for each token. If you increase your vocabulary from 30,000 tokens to 1,000,000 tokens, you are adding millions of parameters to your model that have to be stored in VRAM before the AI even does a single calculation.
You are bloating the memory footprint catastrophically.
Catastrophically.
Oh, wow. So the inventory itself becomes too heavy to lift.
Exactly. And there is an even deeper problem with a massive vocabulary. If you have highly specific, custom-molded tokens, say a token for a very specific, rare medical term, that token might only appear a handful of times in your entire training data set.
So it never learns what it means.
Right. The model won't have enough examples to properly adjust the weights for that token's vector. It will have a very poor mathematical understanding of what that massive token actually means.
You end up with a huge dictionary full of poorly trained definitions.
That's exactly what happens. Untrained garbage.
That is fascinating. So engineers are constantly walking this razor-thin tightrope, make the vocabulary too small, and the sequences get too long, the quadratic math explodes, and your GPU melts down processing the context window.
Spot on.
But make the vocabulary too large, and your embedding matrix becomes a massive memory hog, and your rare tokens are essentially useless.
It is the ultimate balancing act, and it all has to be locked in place before the neural network is even designed. The tokenizer is sitting there, silently dictating the memory limits, the compute efficiency, and the learning potential of everything that follows.
We've taken quite a journey tonight, starting from that initial powerful analogy of the camera lens.
We really have. We covered the often fragile assumption of word splitting.
Right, how relying on spaces is a heuristic that can break down entirely with agglutinative languages or minified code.
And we explored the algorithmic engine room, diving into the mechanics of how BPE relentlessly counts pairs.
While WordPeace tests the statistical likelihood of a merge against a broader language context.
And finally, we hit the wall of vocabulary size.
Navigating that brutal trade-off between the memory footprint of a massive embedding matrix versus the crushing quadratic compute cost of overly long token sequences.
It's a lot to take in, but it's so fundamental.
And the reason we are exploring this so deeply is that for software engineers tuning in, understanding this invisible machinery is no longer optional.
Not if you want to be effective.
When you are trying to optimize prompts, or you are hitting context window limits, or you're trying to figure out why an AI coding assistant completely failed to grasp a specific string of your code.
The answer very often lies not in the neural network's reasoning capabilities.
Right. It lies in how the tokenizer initially sliced up your input.
It fundamentally changes how you approach working with these models once you internalize that the AI is not reading your words. It is reading its own highly optimized, mathematically derived subunits, constrained by a strict vocabulary limit.
It really does. Next time you're sitting at your desk querying a massive LLM to debug a complex architecture, take a second.
It's true.
Imagine that invisible machinery. Imagine BPE or WordPiece silently, instantly chopping your prompt into thousands of mathematical subwords.
Before the model even blinks.
Exactly. And before we sign off, I want to leave you with a lingering question tonight, something to mull over during your next late-night coding session. We established the rules tonight. Tokenization acts as the strict camera lens through which an LLM views the world.
Right.
And we know it is entirely bound by a predetermined vocabulary size built using specific, bottom-up merging criteria based only on the data it was trained on.
Only historical data.
So, what happens when the LLM encounters a completely novel programming paradigm or a brand new syntax that was invented entirely after the tokenizer was frozen?
That is a fascinating edge case to consider.
Are current AI models fundamentally blind to, or at least heavily biased against, concepts that do not compress neatly into their pre-existing
A
tokens?
real possibility.
If you feed it a radically new syntax, does the tokenizer awkwardly chop it up into nonsensical pieces because it is forced to use its old pre-molded Lego bricks? Does the scratched, outdated lens prevent the AI from ever truly seeing the new code clearly?
Something to think about.
Think about it. The photographer might be a genius, but if the lens can't focus on the new light, the picture remains dark. Keep building, keep questioning, and we will catch you on the next deep dive.